At this portion of our course, we're going to modify our knowledge about work and energy for rigid bodies. The work done by a force is calculated by the displacement, and the displacement that we are talking about is the mass center's displacement in this case. And there's our displacement, finite small amount of displacement. By integrating this over the total displacement during this work from 1 to 2, then we find out the work done by this force from an initial position to the final position. However, in rigid bodies, we have such a thing as the rotation, and moment can act on the rigid bodies. Actually, there's nothing as a moment in reality. It's just a force couple. So this is why in this figure we show the formation of a moment by this force couple. This force couple are acting in the opposite directions, and as a result of that they will generate a moment and then make this rigid body rotate. And it might also be in motion, and as a result of that it will move from AB to A prime B prime, and then will rotate as a result of this moment because of these force couples. And the equivalent diagram of this is shown over here, where there's this moment acting in the clockwise direction, and as a result of that there's this angular displacement, finitely small amount of angular displacement that is defined as d theta, and we can calculate this work done by this moment or force couple in this way. If we're going to use the force couple, then we're going to take the moment about this point, and then there's this force acting on it, and the distance of that force is calculated. The displacement caused by that force is this calculated as bd theta. This is due to the rotation, not due to the translational motion, but due to the rotation there is a translational displacement, and this is defined as b theta, or in short m d theta will give us the finitely small amount of angular displacement times the moment, will give us the information about the work done by this moment. And if we integrate it from a theta 0 to some theta final, then we will find the total work done by this moment during this motion. And if it happens that although there's this moment in the clockwise direction, the motion happens in the counterclockwise direction, then the work done by this moment would be a negative work. For example, we could have torsional springs. If you guys remember the spring example, there's a spring and then there's this particle, and if we take a look at the particle, as we move this particle in this direction, there is this motion of dx, and then the force applied by the spring is in the opposite direction. This is the force applied by the spring on the body, and in this case the work done by this force on the body is a negative work, because the direction of motion and the force direction are in different directions. This is the same thing for torsional springs. So torsional springs are something like that, and then you apply a torsion to them, which is the moment, and then if you have a connected body here rotating with torsional spring, then the force applied by the torsional spring is in the opposite direction of the motion of the body, and as a result of that the work done by the torsional spring on a body, on a rotating body, would be negative, as you're compressing it or giving it a tension. Let's take a look at the definitions of kinetic energy of a rigid body. Now that we have the information about the work, now we need to step by step take a look at the energy terms, kinetic energy and then potential energy. If there's a pure translation, then at all the discrete points of this rigid body, if this is our assumption, it is composed of these discrete bodies, all of their velocities would be the same. If it is a pure translation, either curvilinear or rectilinear, doesn't matter. It will be the same velocity. Therefore, the total kinetic energy of this rigid body will be calculated by the summation of all the particles which have the same velocity. So there is no subscript here as VI, because they have the same velocity. And as a result of that, this is just a summation of the mass, the total mass, and the kinetic energy is calculated as the same as you would have for a particle actually. Now, if we have a fixed axis rotation, then the velocity measured at any point will be dependent on the radius and the angular velocity. So if this is mi, then let's say this is mj, then this is rj, and the kinetic energy for this discrete part of this rigid body will be calculated as 1 over 2 mj rj times omega squared, or in these terms we can add up all the terms, and if I rewrite this equation, because omega is constant for, it's the same for all the particles, I can take it out of the summation, and there we will have 1 over 2 omega squared, and inside the summation what we're going to have is mi ri squared. And this is the description actually of moment of inertia about point O, because we define these radii from point O, and therefore this is defined as IO, and I can rewrite this equation in this way. There's another thing I can do actually. I can say this is the mass center, okay, and there is this velocity of the mass center, Vg, and then I can define the points from the mass center to the to these discrete particles, and then describe their locations as some rho I, and then do the calculations, which is the same thing that we're going to do for the next case for general plane motion. So I'm not going to go into details of that, but at the end what we're going to have is, if you remember, this IO is defined as Ig, the mass moment of inertia calculated about the mass center, plus, if we say this is Rg, the radius from the mass center to point O is Rg, then this is mRg squared, right? Now, if I substitute this information here, what I would have as a result of that is the kinetic energy is equal to 1 over 2 mass moment of inertia calculated about the mass center, omega squared, plus 1 over 2 m times Rg omega squared. Now, Rg times omega is actually the mass center's velocity, Vg. So this is nothing but 1 over 2 m Vg squared, which is the velocity of the mass center squared. So this is another way that you might write out the fixed axis rotation's kinetic energy. And this applies to the general plane motion. Now we're going to investigate this general plane motion, and then you will see that we will come to the same type of conclusion. Now, for general plane motion, what happens is that the rigid body moves in a linear fashion. It has a linear velocity independent of its angular velocity. Okay? In the fixed axis rotation, linear velocity is dependent on the angular velocity. How it is dependent? By this radius. But here they are independent from each other. And we can write out the velocity of a discrete particle Vi. It's going to be composed of the rigid body's mass center's velocity. This is Vg, mass center's velocity. And also due to the rotation of this rigid body, rho I times omega, and rho I is defined as this radius from the mass center to the discrete particle I. And the total velocity is a combination of these two velocities. So if I want to write out Vi, it is composed of the mass center's velocity plus this extra term due to the rotation. Now we need to take the square of that. That means dot product of Vi times Vi, by the way. Okay, so that you will get the square. Remember that in the dot product of vectors you will get the scalar, right? This is a scalar, Vi squared. And if you work out this equation, now the last term here is actually the first moment about the mass center, and that is equal to 0. So this last part cancels out, and the other parts is 1 over 2 mv squared, and this is the velocity of the mass center, plus ig omega squared, which is exactly the same thing that I wrote here. 1 over 2 ig omega squared plus 1 over 2 mvg squared. So this is true for general plane motion as well. The kinetic energy of a rotating and translating rigid body will have two parts. One part due to the translation motion, the other part is due to the rotational motion. However, we can still define this kinetic energy as a single term. Take a look at it. What we have done for the fixed axis rotation. It was actually denoted by one term because it had a fixed axis rotation about point O. But then I worked on it, and then I determined it to be defined by two parts. 1 over 2 mvg squared plus 1 over 2 ig omega squared. How did I do that? This one term kinetic energy was defined with respect to this fixed axis rotation. So the question is, in a general plane motion, do we have such a case? We have such a case instantaneously, and we call that location as the instantaneous center of zero velocity. At that point, instantaneously, the rigid body would seem as if it is doing a fixed axis rotation, and the axis is located at this instantaneous center of zero velocity. So, if you could calculate the mass moment of inertia about that instantaneous center of zero velocity, then you can write out this kinetic energy as a single term. And this Ri over here defines the distance to that instantaneous center of zero velocity. There is our rigid body, there is the instantaneous center of zero velocity, and then to each particle you define this Ri. Okay. If you could do such a thing, then you can define still the kinetic energy as a single term for general plane motion.